In the last study guide, part one, we talked about three types of energy. I'm going to call it mechanical energy now. Mechanical energy is any potential energy or kinetic energy. So, ME. So, mechanical energy is equal to the GPE something has plus the KE something has plus any elastic potential energy it has. So, that's a new term, mechanical energy. Now, this right here is the law of conservation of energy. The total energy in a system never changes. It changes forms, but the quantity of the total energy in a system remains the same. So this is true of closed systems. You can't lose energy in a closed system. I mean, it can only change forms. Okay, in an open system, you can lose energy. I mean, energy can leave the system and go to the surroundings. So that's in an open system. Okay, so now, if there is no work due to friction or work from an external force, the mechanical energy will equal the mechanical energy. The total mechanical energy before will equal the total mechanical energy after. That is if there's no external forces acting on the system. Okay, so if no external forces act on the system, whether it's a force that's increasing the energy of the system, we call that work due to big F, or if it's work due to friction, work subscript little f, or drag. If you don't have an external force, you won't have these kind of works happening. Okay, so in a system, any kind of system, mechanical energy will be also conserved. This is not the same as this law, the conservation of energy. Conservation of mechanical energy only applies in either system, closed or open, if there is no external forces, if there are no external forces acting on the system. Okay, so if we expand that equation right there, so we include all the mechanical energy types, all the mechanical energy types added up before there's a change in the system equals the sum of all the different types of mechanical energy after the system changes somehow. And again, mechanical energy is conserved only when there is no work being done on the system, or whether it's adding energy to the system or whether it's taking away energy from the system. Then mechanical energy will be conserved. So I'm going to use ME instead of their symbol of capital E. So if there is work done on the system, the mechanical energy after will be either greater or less than mechanical energy before. So if you have ME plus work due to an external force that's increasing the energy of the system. MEF will be greater than the total mechanical energy before. And if you have a force that is taking energy out of the system, like friction or drag, then the total MEF will be less than the total mechanical energy before. So that W could be W big F, and you could have both. You have external force increasing the energy and drag force taking energy out of the system, turning into heat. It's really not taking it. It's taking mechanical energy out by turning it into heat. And heat is not mechanical energy at all. When you got work through the friction, it's not mechanical energy. It's heat energy. So this whole chapter is going to be about conservation of energy, where MEO plus maybe work, either through friction or through an external force that increases the energy of the system, either one equals MEF. So let's apply this. Okay, so these are like two before and after problems. That's why you know it's a conservation of energy problem. It's just not plugging into a single equation kind of thing. Okay, so here's the mass. Here's the height. How fast speed will be going at the bottom of the track. Okay, you can neglect any friction or drag. There is also no external force pushing it besides gravity. But gravity is part of the system, so it's an internal force. This open system is the earth and the roller coaster with the cart. So gravity is part of the system, so it's not an external force. That's kind of confusing. So what kind of energy do I have at the beginning? Well, I have a height. What kind of energy involves height? Well, that's GPE. And there's no work due to friction, and there's no external force pushing, like a motor force, or someone pedaling it, like a bike. So that's all there is on the left side of the equation. And at the bottom, the height is 0, but at the top, the speed was 0. I should have said that. It starts from rest. Oh, I did. I added that. So at the bottom, the only energy with V, involving V, is KE. So basically, I'm solving for V, so let's break these into their components. GPE is mgh, KE is mv squared over 2. Well, the m's cancel out, so you didn't really even need the mass. So v squared equals 2. I'm going to cross multiply. Then I'm going to get rid of the square exponent. So this would be the square root of 2 times 10 times 80. 800 times 2 is 1600. Well, that works out great because square root of 1600 is 40. So it's going 40 meters per second at the bottom of the roller coaster, the hill. Okay, so in this problem, nothing's said about air drag, so you can neglect air drag. Usually I say that. Neglect, I'll say losses. That's how positive physics does it. Energy losses due to friction or air drag. Okay, now the system is a spring, and the ball and the earth. But the earth really doesn't have anything to do with it because there's no change in GPE. So here's a before and here's an after underneath that squiggle. So what kind of mechanical energy plus work equals mechanical energy final? Of course, it's sigma, but I don't feel like keep on writing that. And sigma over here too, which means total, but I'll just disregard it. Okay, what kind of mechanical energy do I have at the beginning? Well, it's a spring that's smooshed in. So you should see that that's EPE at the beginning. The ball's not moving yet right there. And so what's at the end? The ball is moving very fast. The spring has lost its kinetic energy. So we're talking about KEF here. So K delta X squared over 2 is equal to mv squared over 2. Now, m is not going to cancel out here. Okay, because it's not on this other side of the equation. So m's don't cancel like they did before. I can get rid of the 2 because it's the same on both sides. So, here's the spring constant, K. So, 395. Now, what's delta X? It got compressed from the rest position, 5 centimeters. So, you got to divide by 100. This equals 0.05 meters. You got to divide by 100 because we need meters. Okay, squared equals the mass 0.025 times the speed. That's what I'm looking for. Okay, v squared equals 395 times 0.05 squared divided by 0.025. Then I'm going to take the square root of that mess to solve for v. So I'm getting 6.28, 6.3 meters per second. That bullet comes off the spring. Okay, so here's the before and after problem. Here's the ball moving, and then, okay, so, and then it's at rest. It's just at rest, being caught by the baseball player. Okay, so at the beginning we have KE, and at the end, I'm assuming it was caught at the same height. I have no energy. I don't have kinetic, I don't have spring potential, I don't have GPE. I'm assuming it got caught. Okay, so how much work is done by the baseball player? Okay, this is kind of a clue. So KEO plus work. And I'm going to do a little f because it's like friction. He slowed it down. It's a force acting in the opposite direction. The external force acting in the opposite direction of the velocity of the ball. So it's really, that equals 0. So mv squared over 2 plus work due to friction. I didn't ask you what the force is. I just asked you what the work due to friction is. 0. So, okay, so negative WF is equal to mv squared over 2. Okay, I just rearranged this equation right here. I brought WF to the other side. I subtracted WF from both sides. Okay, and that equals 0.145 times 41 squared over 2. So work due to friction is 128. Native work due to friction is 121.87, so I'll just say 122 joules. So work due to friction is negative 122 joules. That's how much work the guys did to stop the ball. Okay, I did this problem already, something similar to it. So check the QR code to see the right answer. Be sure you change the delta X to meters, though. Everything else looks good. Same kind of problem. Check the QR code for the answer. Okay, so I should make this clear, but I'm looking for the height that this ball gets after it comes off the sprung spring. So what's the height the ball gets? So I'm not given any speed, so I'm really going to have to start right here. And I'll neglect that little tiny 10 centimeters of potential energy. Okay, so right here, I have elastic potential energy. Right here, I have GPE. Okay, because I have height. Right here, because the spring is compressed, I have EPE. So they didn't say anything about any drag or anything like that. Or the spring force, you might say that's an external force. But no, the spring is part of the system. So it's not an external force. You might say gravity is an external force. No, the Earth is part of this system. You can assume that. Okay, so we can say the total energy before equals the total energy at mechanical energy after. So it's EPE at the beginning equals GPE at the end. So we got K delta X squared over 2 equals MGH. And we're looking for the height. So let's divide both sides by mg k delta x squared to mg equals h. So all I did was I multiplied both sides by mg. Okay, then you can solve it. So I plug my numbers in, and don't forget to change the 10 centimeters to 0.10 meters. And so I'm getting 22.5 meters. So the choice is, not right. Oh, okay. So I got my picture showing 10 centimeters when it's supposed to be 3 centimeters. Wow. See? 0.03 meters. So I don't really even have to convert it. It's already in meters. So let's change that. So sorry about that. I get 2.03 meters. Okay, so they used 9.8, so they got a little different than me. Okay, this is the same problem. I guess that's where I got my picture. So you can do it and check the QR code there. This one, if the picture was there, it would have helped. Okay, so it shot upwards, but it's not like the problems we just did. So here's the ball with a squish spring, and then here it is coming off that spring after the spring potential has lost its energy and giving the ball kinetic energy. So basically, all you do is, what kind of energy do you have at the beginning? Last potential energy what kind you have at the end, KE, and you can disregard the little tiny bit of potential energy that it gained. Let's just try this and see if it's a difference. When it's that small, it's not going to matter. So you could say KE plus PE, GPE, if you made that your zero reference line, but I'm just going to do a simpler case. So let's see if that works. So K delta X squared over 2 equals MV squared over 2. 2's cancel out. So let's get rid of the M. So divide both sides by M. And then square root that to get rid of the V squared of the exponent. And so I put those values into that equation, and I get 9.8 meters per second. And so they have an answer there. If you think, well, Mr. Noyes said potential energy could have had a factor, well, let's see what it is. GPE gained by the potential energy of the spring is equal to mgh, which is equal to the mass, 0.002, times g is 10 meters per second squared, times the height is 4 centimeters, 0.04. That comes out to be 0.0008 joules. So that's insignificant. So whenever you have these spring problems and you're given a delta x, use that delta x for the spring potential energy equation, but don't use it for a height. And then GPE, don't, because it's insignificant. Okay, so you can check this one. Obviously, if it started from rest up there, GPE at the beginning is equal to KE at the end. And you can figure it out like I did earlier on. Same thing, check the QR code. Okay, so again, here's the delta x. So it's dropped the distance of 1 meter. So from here to here is the height of 1 meter. Don't add this insignificant 2 centimeters as make that part of the height. It just is an annoying thing that doesn't matter. Okay, so what kind of energy does it have at the beginning? It has height, so that's GPE. What kind of energy does it have at the end? Spring potential or elastic potential energy. And so that'd be mgh equals k delta x squared over 2. And so we're solving for what? The spring potential energy. Okay, well, all that is, I don't have to break through all that. Oh, wait, no. I'm solving for the spring constant, which is K. So, let's clean this equation up right here. Cross multiply 2mgh, and then divide through by delta x squared. That's what K is. Okay, so I plug in my numbers. Don't forget to change the 2 centimeters to 0.02 meters. So I'm getting 250,000 newtons over meters. So that is one stiff spring. And there we go, right there. Same kind of problem. Check that QR code. Okay, this is the same kind of problem that we did before with EPE original equals KE at the end. Now, notice there's no external force acting on this. The spring force is an internal force. So use the QR code to find the answer. Same as that question with different numbers. Use the QR code. Okay, we did this problem with the baseball that was caught. So we have a bowling ball that's moving. So that's KE, but then it stops. Energy can't just go to zero. The final energy is stopped. It's not rolling up a ramp. It's not rolling into a spring and compressing it. It's just stopping. So that's because there's work due to friction or something else stopped it. So how much work is done? So work F equals negative KE, and they left the negative out. They should put negative in all the answers. Okay, so that's negative mv squared over 2, 5 times 10 squared over 2. So we're looking at 50 times 5 is 250 joules, but really it's negative. Same problem. Check the QR code. Okay, so the spring has no energy at all at the beginning. So the mechanical energy original equals mechanical energy final plus any work. Maybe there's work. Of course, there's work. They're asking for how much work is done. So original mechanical energy is 0 because the spring was not compressed at all. The final mechanical energy is the EPE. So the work due to an external force pushing it closed, it's not negative because it's adding energy to the spring. Okay, so work is the gain in the EPE final. So basically, it's a lot of writing for something very simple. K delta x squared over 2 equals 450 times 2 centimeters. Change it to divide by 100. Square it. Divide by 2. I get 0.09. Okay, 0.09 right there. Okay, we did this one already. So the spring has no energy at the beginning, so the beginning there's nothing. At the end we got compressed spring, so there's EP, elastic potential energy. So positive work had to be done to put energy into the system, the spring. Outside force is you pushing the spring. Okay, so work just simply equals K delta x squared over 2, like we've done before. You can check the QR code. Okay, the whole point of this problem is to do letter E, but we got to do all these steps leading up to letter E. Okay, so draw a free body diagram for the box. Okay, here's the box. Here's the applied force. I'll call it big F. That's 230. There's friction, so friction opposes that. Okay, we're going to have to find what that friction is. Let's do it now. So that friction, before I do that, you also have weight. You have normal force, but they cancel each other out. Okay, so normal force would equal the weight. So friction equals the coefficient of friction times the normal force. Normal force equals weight. Okay, so the frictional force is equal to the coefficient of friction, which is 0.3, times the weight. The weight is 46 kilograms times 10, which is mg. So the coefficient times mg, 46 times 10. So I'll just say 460. And I get 138 for the friction. Okay, the big force, the applied force is 230. So I'm going to ask you right now, what's the net force? The net force equals the 230. The applied force minus the frictional force. This is all a review of what we did before. 230 minus 138. That equals 92 newtons. Okay, why did I do all that? Because I want to find the acceleration of the box. So let's do letter B. You know that net force equals ma. So net force is 92. The mass is 46 times A. A comes out to be 2 meters per second squared. Okay, so how far will the box go in 15 seconds? So that's delta x. So we're going to have to use the kinematics equation. How about delta x equals VOT plus AT squared over 2. So VO is 0. I said that at the beginning. It started from rest. Okay, so it knocks out that term. A we just found is 2 times 15 squared over 2. So I get delta x is 225. It's a lot. Okay, so let's do letter D now. What would be the velocity of the box after 15 seconds? Well, I'm going to use another kinematics equation. So how about A equals VF minus VO over T? So 2 equals VF. This is what I'm solving for, the final velocity. VO is 0 over 15 seconds. So VF equals 30 meters per second. And finally, what's the kinetic energy of the box at the end of the 15 seconds? So I just use the generic equation. So the mass of the box is 46 times the speed of the box is 30 squared over 2. And I'm getting 2,700 joules, which I'd probably round up to 21,000 joules. Okay, that was a good demonstration of how all the laws of physics tie together. I've been teaching you individual units, but they're all related. All these equations are related. So give you appreciation for that. On a test, I would not give you something like this. But I could say, what's the kinetic energy at the end without having to do all this junk? And that would be possible if I gave you the delta x. So you wouldn't have to do any kinematics equations. The delta x. Okay, this nightmarish problem continues. How much work is done in this first 15 seconds by the following? Applied force. So F, the work done by the applied force F Well, work equals big F times delta X. Okay, so it's 230 times, we found to be 225. So 230 times 225. I get 51,800 joules. Okay, by the friction force, the work done by the friction force equals little f times delta x. So that's negative 138 times 225. I get 3100. 2, 3, 4. 31,000. So that's negative 31,000 joules. Okay, what's the work done by the normal force? Well, because the normal force is perpendicular to the displacement, there's no work is done, 0 joules. Same with the gravitational force, no work is done. Okay, remember when a force is applied to an object and the displacement is perpendicular to that force, cosine of 90 is 0. So no work is done. Okay, what's the work done by the net force? Well, the net force is equal to 230 minus 138, the sum of the forces, the applied force and the frictional force, which we did before. 230 plus a negative 138. And I get 92. That's the net force, but what's the work done by the net force? The work done by the net force is equal to the force, the net force times delta x, 225. That equals 20700, 20,700 joules. Compare the work done by the net force and the final kinetic energy. Well, it's supposed to be the same. Okay, so what we have is the work due to the external force plus the work due to the friction plus 0 because the box had no energy at the beginning equals the kinetic energy at the end. Okay, this is 0. And this is the same thing as net work that was solved up here. Let's just check. If you look back to the page we just did, this answer that I just solved here is equal to the kinetic energy final. How much power did the pusher expand? Okay, well, power is the work over the time. So you got to go with the work that he put in. The work that he put in, which was right here. Where is it? 51,800. 51,800 divided by 15 seconds, joules per second. So I get 3,450 watts. That's watts. Capital W is watts when it follows the number. How much power is wasted due to friction? Okay, you do the same thing. Work due to friction. And so the work wasted as friction we did up here, 31,000 divided by 15 seconds, joules per second. That's watts. So 31,000 divided by 15, you lost 2070 joules was lost. I mean, not joules, joules per second, which is a watt. I'll put negative showing that was lost. Okay, these last few pages I skipped right here. We'll probably be doing that one in class as an example, so I won't do it right now here, but it's just like the one we just did. Okay, so this is two problems in one. Find the initial potential energy of the block. So that'd be GPE equals mgh. The mass is 350 grams, but you gotta have that in kilograms, so divide by 1,000. Can't use grams. G is 10, H is 110, but you're gonna have to divide by 100. So I'm getting 1.10. I get 3.85 joules. Okay, find the speed of the block at the bottom of the loop. I should just say speed. So right here, what's the speed down there? Well, it has to do with kinetic energy final. Let's say right at that position. So do you see that the GP at the beginning has to equal the KE final, where I have it marked with the X? So, I mean, I think it'd be easier to just start from scratch because the masses cancel out. And so V is equal to GH square root. What I did was cross multiply and then square root both sides. Okay, 2 times 10 times 1.1. Okay, 20 times 1.1 is 22. Square root 22, which equals 4.69 or 4.7 meters per second. So that's the speed at the position marked X. Find the velocity of the block at the top of the loop. So right here, I'll put a triangle right there to indicate that. So, I mean, you can do this several ways. You can say, okay, it's moving there. It's moving as well up there. So, let's do a different color. Okay, so I'm going to do letter C right here in blue. Okay, so I got GPE at the top, at the very beginning. So GPE original equals KE at the triangle plus, I'll just say final, at the triangle plus GPE at the triangle. Okay, so I already have GPO 3.85 from step A. So 3.85 over here equals mv squared over 2 at the triangle plus mgh at the triangle. Now, h at the triangle, the radius of that circle or loop is 15. So the height is the diameter or twice the radius. So that'd be 30 centimeters or 0.3 meters. So what's the mass? 0.35. Okay, times v squared. I don't know what that is. That's what I'm trying to solve, over 2 plus 0.35 times 10 times 30 centimeters or 0.3 meters. So I did a little calculation there. Let's isolate the v squared on one side by subtracting 1.05 from both sides. Okay, now divide both sides by 0.175. And then take this. Okay, so 16. So v comes out, the square root of 16 equals 4 meters per second at the top there, compared to at the bottom 4.69 meters per second. Okay, so that's the answer of letter C. Okay, so this problem I'll probably do in class because it's just like the one I just demonstrated. Okay, these problems we're going to finish off with are interpreting F versus delta X graphs. Now, we use these for springs to figure out the area between the line and the x-axis. That area would have been the elastic potential energy, but it doesn't have to be that specific. It can be work. The area between the graph line and the x-axis of F versus delta X graph is work, net work. So let's look at letter A. How much work is done by applied force as the car moves the first 10 meters? Okay, so I don't know. I'll try to do this carefully. So the first 10 meters, it looks like it's just this area right here. I'm just approximating. That looks like it's 18. So I got triangle, base times height divided by 2. Base is 10. Um, 10 times the height, 18 divided by 2. So that's 9 times 10. 18 divided by 2 is 9 times 10, so that's 90 joules. Determine the kinetic energy of the car at the 10-meter point. Well, the work I did to push the car is equal to the kinetic energy, the change in kinetic energy. So the original kinetic energy was assumed initially at rest. So this be KEF minus KEO. But KEO was 0 because it was initially at rest. Okay, so that's the same answer, 90 joules. What is the velocity car at the 10-meter point? Well, I just do KE equals mv squared over 2. So KE, we just said, was 90 equals m 4.6 kilograms v squared over 2. And I would cross multiply, so it's 180, and then divide by 4.6, and then square root of that. Okay, and so I get 6.3 meters per second. That's how fast the car is going at that point. What is the total work done by the force of moving the car to the 30-meter point? Okay, well, the area under the triangle, that big triangle, the whole triangle, that entire area would be base times height times divided by 2. So it looks like the height is 20, the base is 30, then divide that by 2 because of the triangle. So 10 times 3 is 30 times 10, so that comes out 300. 10 times 30. Okay, so now let's do letter E. What is the velocity of the car when at the 30-meter point? Okay, I have the kinetic energy already from letter D, which is the total work done. Okay, so what I'm going to do is just do KE equals mv squared over 2. 300 equals, what's the mass of the car? 4.6 kilograms. V squared over 2. So we've done this before. So V equals 300 times 2, cross multiply, divide by 4.6, square root. So I get 11.4 meters per second. Skip this page. So you should be able to do the last 3 pages based on the example I just showed you. You guys should be able to do this one by now. Basically, find the vertical height. That's probably what I'll ask you to do. Find the height at the end right here that it attains. And this is easy because it's frictionless. There's no friction. So really, what kind of energy do you have at the beginning? EPE. What kind of energy do you have at the end if it stops at the top? So what's the highest height it makes? Okay, so that's GPE. So very simple. K delta x squared divided by 2 equals mgh. Now let's see if they gave me the K. Yes. They give me the delta x. Yup, but you got to change that to meters divided by 100. So you got everything you need. You're solving for h, right? The mass is given of the block. Yes. Okay, so you can finish that one. Okay, so let me just revise this problem a little bit. So here's the floor, the tabletop, I mean, and then here's that. Let's say this distance is 2 meters right here. And I don't know what that distance is, but it doesn't really matter. Okay? So the block is moving, and there's going to be friction on the block this time. Then it's going to end up here at rest. And we're supposed to find the height gained. It's going to be less, right? The height gained is going to be less because there was friction acting in this tabletop. But up here, the ramp is totally smooth, frictionless ramp. Okay, find friction between block and the table. So F equals mu n is between the table and the block. The coefficient of friction is 0.3. Normal force is mg, or the weight. Okay, the mass is 0.15. I just looked at the previous page, and g is 10. So that comes out to 0.45 newtons of friction when it's moving across the tabletop. Find the work lost due to friction. Okay, the work lost due to friction is going to be negative always. So it's F times delta X. We just found F, 0.45 times 2. That's what the distance is. Delta X. Not the delta X for the spring. The delta X for the distance that the block traveled on the table. So that comes out to be 0.90 joules. Find the GPE attained. Well, it has, okay. So what kind of energy did it have at the beginning? EPE plus work due to friction. Actually, it's minus because equals GPE. So I just inserted the picture from the problem that we did a few pages back, or set up. Okay, so I could get the data here. So EPE original is K delta X squared over 2. Okay, K delta X. K is 56. Okay, because I just designed this problem, let's change this 56 to 560, because I'm not going to have enough energy at the beginning if I use 56. So this is, K is 560 instead of 56. Delta X is 6.4 centimeters, or 0.064 meters squared divided by 2. Work due to friction, I have it up here as negative 0.90. So that will be my GPE at the end. So I get for GPE final 0.25 joules. So we can now figure out what the height is. So GPE equals mgh. So 0.25 equals the mass, 0.15 times 10 times h. So h is equal to 0.25 divided by 1.5. And I get 0.17 meters, or 17 centimeters high. Okay, so if you have friction, it's more of an annoying problem.